graded homework, yes.
So, what is the current to this equal to the current to this?
Yeah.
Which means that I is equal to what?
Yeah, just maybe
I mean,
To I is equal to C dV by dt, right?
what?
I is equal to C dV by dt, right?
Yeah.
Because current to this equal to current to this.
Okay.
I already got that one.
I have a whole bunch here too. I think it's hard, right?
Oh no, that's homework 3. Oh no, mine's you didn't do that. Yeah, homework. You got my homework 4.
No, I hate checking.
I didn't homework 3.
It takes the easy to without and so.
Two ten and 211. Guess the largest one. I think 1 and 1. No, so 2 10 211 are all in the same class. Are all in the same class.
They
Are we in 211?
secure. So they have one class in the end.
You are in 210.
Exam here, some of you have not picked up your exam, so I put them in front of the desk. I have a few high scorers here, haven't picked up the exam. Is Ying Wang here? No? And then Andrew Weiner? No? And then Ying Qiu Li? No?
Please submit original homework.
And regrade is due this Friday. If you want your exam wants to be regraded, please send them in this Friday. Write your request on the sheet of paper and then attach that to your exam sheet. Okay, let me put it down.
Hey, this is the first time the grader said, like, please submit original homework and not a printout. But I do it on my tablet, so this is like the original.
Okay. And don't write on your exam sheet, okay? Write on the separate sheet when you request for a regrade. Otherwise it might be for features for a regrade. And so let's have
Did you connect it?
let's get started with what happened to the 2 students who used to sit here? Ramesh and Rawat, was it right? Where did they go?
They didn't do too well in the exam.
Okay.
They're gone.
They're gone?
I'm
They were very studious, sitting right out here. I thought maybe they're scared of me right now.
Professor,
Yes?
did you say these were by net ID or last name?
Last name.
That should be last name, right? You taught them by last name?
I think it's last name.
Last name.
should be the same, right?
That. No.
Depends on how much.
The initial bad idea and the initial the last name. Same. No? Mine just.
For you. I can't generate.
So today I'm supposed to do section 4.2.2 of the textbook. Okay, section 4.2.2. Going to be source transformation and superposition methods. Okay, source. Okay, so what is the first thing that you have to do in this phasor technique? If you're given the circuit, what is the first thing that you have to do? Write out the phasor circuit. Right? Write out the phasor circuit. That's the very most important thing. And there's in mathematics you will say a homomorphism. Homomorphism between phasor circuit and resistor network, resistor circuit. So if you have a purely resistive circuit, you can actually learn all the techniques without having to solve any ODEs. You have Kickoff Current Law, Kickoff Voltage Law. And it turns out that in phasor circuits, you have the same thing, except that now your resistors are replaced with impedances. Okay, there's a major transformation. All the sources will be equivalent, will be replaced with their phasor representation. Okay, and then Kickoff Current Law and Kickoff Voltage Law still hold true. And you see that very easily. Say if I1t plus I2t plus I3t is to the 0, say this is KCL. And if I write the phasor equivalence of this, it would be I1 e to the j omega t. This is I1t can be written in that form, and then I2 can be written in that form. And then I3 can be written in a similar form. And you must all add up to 0, and you can consolidate all these three equations, plus I2 plus I3 e to the j omega t must be equal to 0. But this is going to happen for all of omega t and t. This is something that goes round and round in a circle on the complex plane. Okay? So in order for this to be true, it must be that whatever that is in the parenthesis must be also equal to 0. So I will have I1 plus I2 plus I3 e to the j omega t must be equal to 0. But this factor is common to all of them because they all have the same omega. It's very important. All the phasor quantities have to come from the same frequency. And once you establish that, you have I1 plus I2 plus I3 must be equal to 0. And hence KCL holds true as well in the phasor world. And similarly, KVL, you have V1t plus V2t plus V3t equal to 0. By the same token, you have V1 plus V2 plus V3, which are the phasor representation of V1, V2, and V3. They must also add up to 0 if they have the same frequency. Okay? So let's do some of this again. And so if you have a phasor, well, you can also have source transformation. Just like resistive networks. Okay, we saw this in resistive networks and resistive circuits. You can have that also. Except that you have to remember to think about phasor quantities instead. So you might have a source that is like this, and which we usually call what kind of equivalence in the resistive network world. What kind of equivalent circuit this is? Thevenin. Okay, this is called a Thevenin, and in the phasor world you will have that as well. And then you will have another one very similar to the resistive network case. And then this will be plus B. Let's call this B. Okay. And how would you find the Thevenin voltage for this kind of, it is a Norton equivalence. How did you find the Norton voltage or Norton, the Norton current in the Thevenin voltage? This would have been called the Thevenin voltage. This would have been called the Norton current. How did you find them? Yes, yes, very good. You actually find the short circuit current and open circuit voltage, just like you had before. Okay, V Thevenin is V open circuit, I Norton is I short circuit. And then R, this is actually the Z Thevenin. Okay, this thing can be also called Z Thevenin. This is also Z Thevenin. Is equal to what? If you were to draw a parallelism of homomorphism as to what you have learned in resistive network, what would this number be? You will be dt over In, right? Or B open circuit over I short circuit. So simple as that. Okay, are there any questions on this source transformation technique? If not, let's do an example so that you can do your homework. Okay, let's do example 415. And I have a circuit that looks something like this. But I'm drawing the phasor circuit right away without having to draw its original circuit. And then I have a capacitor here, which has an impedance of minus J2 ohms. And then I have the resistor here. And you are to find the Thevenin equivalence of this circuit. Okay? What kind of tricks can you pull in order to solve this problem? This is 2 ohms. This is 4 ohms. Okay? One thing we can do, actually seeing these two combined together, is to convert this into a Norton equivalence. Okay, convert that into a Norton equivalence and replace that with something like a resistor here, a current source there. Okay, before we connect this part to the rest of the circuit. But in order to find that current there, you just need to find the short circuit current of this part. What is the short circuit current of this part? Vs over 2. So this Norton current must be Vs over 2. And what is the resistor that you should hook over there? 2. Very good. 2. Okay. And then you hook the rest back up. And then this is Is. And then you have this quantity over here, which is minus J2 ohms. And then you have that over there. And you can keep consolidating things. You can actually now put this together. Okay, these two currents are connected in parallel. So together they form a total couple. Yes, there should be a resistor there. You're correct. Thank you for pointing that out. Okay. The next thing you can do is to consolidate these two sources. So they're in parallel connection. So you can replace them with just one source. And then with a resistor that looks something like this with 2 ohms over there. A capacitor with an impedance of J2 ohms. And then let me not forget the resistor this time. So tell me what this current should be. Very good. Vs over 2 plus Is. This is a consolidated source. And now I can replace this. Actually, I can consolidate these two impedances by parallel connection and combine them into one. So, Z parallel is 2 ohms. Usually, sometimes you see this notation, parallel connection with J2. Okay, if you connect these two impedances in parallel, you can use a parallel formula, or it can be just Z1, Z2 over Z1 plus Z2 kind of formula. Okay, and if you do that, then you would have minus 4J for the numerator. And then you have 2 into 1 minus J for the denominator. Okay, and then you bring the reciprocal upstairs. You bring the denominator upstairs by multiplying by 1 plus J. 1 plus J. Okay? And what you have in the denominator is just A squared plus B squared, which is 2. So you have 4. You have minus 4J into 1 plus J divided by 4. Cancel each other. And what do I get now? Minus J times J is 1 minus J. Okay, so the parallel connection is very simple. Just 1 minus J ohms. Well, what do I do next now? So I can replace this with a parallel connection. And if I ask myself what the Thevenin equivalence of this part would be. Okay, what the Thevenin, yes?
Would that be a negative 1 minus J?
Let me check my thing.
No, it's just 1 minus J.
There's a negative sign.
This is,
I see.
I have 1 minus J.
It's right.
That's right?
It's right.
This negative J times J gives me 1. So I have 1 minus negative J. Right? So I'm correct. Yeah. I make errors, but I'm correct this time. Okay? Thank you. So now what I need to do next is to actually replace this part. This part is just the current source in parallel connection with an impedance. Okay? So the first thing I need to do is to find the open circuit voltage of that part. So I need to find the open circuit voltage from that part connected to an impedance which is just 1 minus J.
Plus 4.
Okay? So the R Thevenin is quite clear. R Thevenin is 1 minus J. Right? If I was to find the Thevenin equivalence of that. What is the V open circuit? V Thevenin. Right, it will be that impedance, 1 minus J, which is the totality of this. This becomes 1 minus J ohms. Okay, when these two are connected in parallel, then the open circuit voltage is just this current times that thing over there. So this would be 1 minus J Vs over 2 plus Is. And that is the open circuit voltage, and this is V Thevenin. Okay?
Shouldn't you add the 4 ohms also?
Add what?
Add the 4 ohms?
Oh yeah, I should have a 4 ohms here. This should be an impedance. Sorry. This should be an impedance, and this should be the 4 ohm. Okay? So this thing would be equivalent to. So finally, the equivalent circuit would be this one. Rather complicated looking. 1 minus J Vs over 2 plus Is as the driving source. Okay, and then an impedance over here. And that impedance is 5 minus J ohms. Okay, that would be the equivalent circuit. Okay, and then you can figure out what the open circuit voltage is and what the short circuit current is. Okay? So that is example 415. Any questions regarding this example? So it's quite straightforward. As long as you keep your bearing correct, hold your compass, so that you know how to distinguish between complex numbers and real numbers. Okay, that you are actually working with phasor quantities, that everything has to be at the same frequency, cosinusoidal, sinusoidal, time harmonic, CW, constant wave, there are many names for that. Okay, monochromatic signal, and all that refers to a time harmonic signal.
Professor,
Yeah.
I think another point to mention is that the phasor method doesn't give you the transient information, because some students are getting confused.
Oh, the phasor method is only for sinusoidal signal. Okay, sinusoidal signal, or in this book they call it cosinusoidal signal, time harmonic signal, and it does not have a transient signal. You will learn how to do that when you reach Fourier transform. Okay, you will learn how to do that when you do Fourier transform. Mr. Fourier came up with this very important theorem. It says that all signals can be written as a sum of sinusoids. Okay, as any signals can be written as sums of cosinusoidal plus sinusoidal function. N is equal to maybe 0 to infinity. Okay, he has this very important theorem. This is called Fourier series, and it was done by Joseph Fourier around maybe 1780s. Okay, just before the French Revolution. So he fought for the revolutionaries. He made cannons. And then he discovered this very important theorem. And there's a Fourier law, there's a Fourier theorem, Fourier series. And I read that he finally accompanied Napoleon to go to Egypt. He lived in Egypt for a while. So when you visit his tomb in Paris, you see Egyptian symbols, the Egyptian sign, because he lived in Egypt for a while. Okay, that was him. So as long as you know how to solve problems with this as driving terms, you know how to solve problems with arbitrary signal by the principle of linear superposition. Okay, so let's do the other example. Example 416. And you are supposed to use the principle of linear superposition to solve this problem. You're given this rather complicated looking problem that looks something like this. J4, and then you have a voltage source minus J2, 2 ohms. These are all in ohms. Impedances have units of ohms since the ratio between voltage and current. Okay, so you're asked to find the open circuit voltage and what this should be. Okay, and you can actually use the principle of linear superposition if you want to. You don't want to, that's fine with me. Okay, you can do it by umpteen methods. You know how to do this for resistive networks by many means. Okay, pick one that's best for you. Okay, this is IS. As in your exam, you were asked to find the output voltage as the linear superposition of the current source and the voltage source. And many of you came up with different ways of doing that. Okay? Let me see. There is a resistor of 2 ohms over here. Okay? So we can find the open circuit voltage quite easily. Okay, V open circuit is equal to, if you were to just assume this loop to do our KVL, if you just do this loop, V open circuit must be if you have this current source over here, if that is open circuit, the current has nowhere to go. This current has to go like that. Okay? If that is an open circuit, so you immediately realize that the current that goes through the J4 inductor must be IS. Okay? So you would have the fact that V open circuit is Vs plus this voltage drop. That voltage drop, if the current is flowing in this direction, is IS times J4. Okay? So that is the open circuit voltage right away. And then you can find the R Thevenin. This open circuit voltage will be V Thevenin. And then R Thevenin, you can do that by the test signal method. You can shut off all your sources and ask what kind of impedances do I see when I look in this direction. If I shut off the current source, what does it become? Open circuit, very good. If I shut off this one, it becomes a short circuit. And if you look at the circuit now, that would be just something like 2 ohms, J4 impedances, 2 ohms, and then the short circuit. Okay, the short circuit is going to short out this part. This part plays no role anymore. Okay, so you're going to see only this impedance or resistor of J2 plus this impedance. So RT is equal to 2 plus J4. Okay? Yep, I got that correct. RT is going to 2 plus J4 ohms. And then now you don't even have to find the short circuit current. You can find the short circuit current, which is I Norton, okay, by dividing 2 quantities. Okay? That 2 quantities is just the ratio of this. Okay, V Thevenin over R Thevenin. Okay? So that is example 416. Are there any questions on this? Rather straightforward, if you keep your bearing straight. Yes?
Why do we ignore the 2 ohm resistor when we're doing open circuit, the one in the middle?
The 2 ohm resistor.
Yeah.
When this is open circuit, this current will flow this way. It will flow this path instead of throwing this impedance. So these 2 have no role to play in the total impedance of the circuit. Okay? Any questions now?
Can you go over again how you got the open circuit? Sorry.
Open circuit voltage, right? This one, right?
Yeah.
Well, that open circuit voltage, if this has to be open circuit, will be the voltage I get by applying Kickoff voltage law on this loop. Okay, on this loop. And so you say VOC must be this voltage drop plus this voltage drop plus this voltage drop. Okay, this voltage drop is 0 since there's no current flowing through here. And then this current must be forced to flow in this direction only. So this current must be IS. And then you have IS times J4, and this voltage is just Vs.
Okay.
Okay?
Thanks.
So you get that to be the open circuit voltage. Any other questions? Yes?
Why isn't it minus J4 since the current's going the opposite direction or it's going the same direction with the loop, but if you put the polarities on the inductor, it's going.
So if the current is flowing this way, this is a voltage drop of I times the resistor, but since I is 0, there's no voltage drop. If the current is flowing that way, then the voltage drop is like this. Okay, this part is higher than that part, and that voltage drop is Is times J4. Okay, think resistor network, because imaginary numbers have no directions, right? Imaginary numbers are abstract. But replace them with resistor network in your head if you think about this voltage drop thing. Because if you think about those phases, then things get very complicated. Use homomorphism of this with the resistor network to do your problem. Okay, think of this as a resistor. What would the voltage drop be? Then it is Is times that resistor. But now you replace that resistor with an impedance. Okay, and then this is the voltage drop also. So this voltage drop must be equal to this voltage rise. Yes?
So after you changed it to an impedance, then it doesn't have a time dependence?
That's right. Because impedances are defined to be ratios of phasor quantities. And the relationship between time dependence quantities and phasor quantity is this. Okay, IT is equal to real of I. So you have to keep your bearings straight. Okay, think of these quantities as something in the complex world, in the complex number world, that if you multiply by e to the j omega t, and then taking its real part, you get a time domain quantity. You get a time dependent quantity. Same thing for the current. Think of them this way. This B and this I are independent of time. Very important. They are independent of time. They're just complex numbers. Okay? So when you look at this impedance, it's just a ratio of two complex numbers. Those complex numbers come from there. And then this has to be a time independent quantity. It's just a constant independent of time. Okay? So keep this bearing very straight so that you can realize and apply your homomorphism rule. Okay? Are there any other questions? Okay, if not, let's do the next example then. I had example 416. Then I have another example that uses a rather complicated locking circuit. And that circuit looks something like this. 2 ohms, and then I have a voltage source over here. 2 volts with a minus sign here. And then I have a current source over here. J amperes. Okay, J amperes. And then I have an inductor, J2 ohms in impedance. And then I have a capacitor with minus J2 ohms in impedance. And then I have a resistor. Okay, you're asked to find the V Thevenin. This is 1 ohm, 1 ohm I believe. Okay, so why is the impedance of an inductor always negative? Why is that so? You might wonder why.
1 over j is 1 over j.
Why? That's right, very good. Z of a capacitor is 1 over j omega c. So this makes it minus j over omega c. So it's always negative. Z of an inductor is j omega L. So it's always a positive quantity. Okay, so when you see a negative sign over here, it must be wrong. If you see a positive sign here, you're probably very wrong. Okay? Okay? So let's see how we can solve this problem. (417). So we write the Kickoff Current Law, and we can write Kickoff Current Law at this node first, for instance. Okay? Then I call this node voltage V1. Okay, and I can call this node voltage VT. Okay, V1 plus 2, V1 plus 2, which is the voltage at this point, Okay, that voltage node there must have V1 plus 2 divided by 2. That gives me the current going in that direction. Okay. And then I need to find the current going in that direction. Okay, that current is V1 minus Vt divided by J2. Okay, that current goes in that direction. And then that must be equal to the current coming into the node. Must be J. Okay, this is Kickoff Current Law at node 1. And then I need to write Kickoff Current Law at node 2. Okay, then I will have Vt. So this is node 1. And let me call this node 2. Node 1. Okay. Node 2, the current that is flowing in that direction is Vt minus V1 over J2. Okay? And then the current is flowing downward. Assuming that I have a ground here, would be Vt divided by J2. And that must be equal to each other. It must add up to 0. Okay, so you have this quantity that Vt minus J V1 divided by J2 plus this quantity must be equal to 0. This equation means that the Vt terms cancel each other. The Vt term cancels each other. And you're left behind with just V1. So what must the value of V1 be? 0. Okay, V1 must be